Welcome back. Section 6.2 Exponential functions and their derivatives. Let's start with the definition of an exponential function. Let b be a real positive number. Notice we are looking at a real number, base, positive. An exponential function with base b is the function fx equals b power x for any x in real number, the set of real numbers. So first of all, notice we want b to be a real number because we want f to be a real value. If I place in a complex number here, this does have a meaning, but it takes some work to understand it, and it's no longer a real valued function. Moreover, I don't want b to be a negative number, okay? Because you know exponent can be fractions, say 1 over 2. What's the meaning of power 1 over 2? It means square root. So square root of a negative number will land you in complex case. So to make things real, to keep things real, you're letting your base b to be a real positive number, and this is your exponential function base b. To understand this definition, first note what is b to the power n? That is, n is a positive integer, okay? So positive, whole number. Well, it just means b times b times b, where b appears n times. Okay, so you took care of exponents which are positive integers. What about exponent that's 0? B to the power 0 is 1. Now this again is important. See, b is positive. If b were 0, 0 to the power 0 is undefined. But something non-zero power 0 is 1. Now, what happens when you have a negative integer, right, as an exponent? So let m be negative n, where n itself is positive. So that means m is negative. So b power m is b power negative n, which is 1 over b power n. We already know what b power n is. So 1 over b power n we know. This is how b power a negative integer is defined. Now, so we have covered integers so far. Positive integers, 0, negative integers. Now what happens when you're rational? P over Q, right? So for good measure, consider the case where this is least, you see there is no common factor, okay, reduced fractions. It doesn't matter. Suppose you take a fraction, so that's a rational number. P, Q are integers. Assume Q is positive. Assume that the denominator is positive. Okay? Why? If it's negative, well, just move the sign up. We are allowed P to be negative, but Q, make sure it's positive. Then, what is B power this rational number? B power X is B power P by Q, and it is defined to be qth square root, so denominator root of the power p. So you know the meaning of b power n integer. That's what we defined earlier. So b power p, you know, take its qth root. All right. This is equal to qth root of b, then a power p. So now this equality, it is important to note that we are relying on the fact that b is positive. Okay, if b were negative, this is not a guarantee. This is not a given. You can check with some examples. So this is how you would define exponent, where the exponent is a rational number. So it's a fraction. Denominator root, numerator power. All right. Now, if you have so notice we took care of all the integers, Now we have also taken care of all the rational numbers, positive or negative. What about irrational number? Well, there is a result in analysis, or this is exactly how irrational numbers are defined. What is an irrational number? Well, you will find a sequence of rational numbers converging to it. Okay? So given any irrational number, you are guaranteed to find a sequence of rational numbers converging to it. So b power x is then defined to be limit r approaching x. So take that sequence, and for each rational r, find b power r. So you get a number here. So as the rationals converge to x, find the limit of b power r. Where it converges, that is what is defined as b power x. Now, we are hiding away a bunch of information here, okay? That this limit should exist and so on and so forth. Well, this is a well-studied topic. So in analysis, real analysis, so let's take this as a definition. For an irrational real number x, b power x is defined to be limit r approaching s b power r. Okay, where r, the set R, is any sequence of rational numbers converging to x. Here are some examples. The blue curve is 2 power x. The red curve is 3 power x. The purple curve is 1/3 power x. Half power x is the green curve. So notice there is some symmetry going on. 2 power x and half power x, they are symmetric about the y-axis. Indeed, they are. Because half power x is nothing but 2 power negative x. So if I change the sign of x from positive to negative, I have to reflect it, and that's what has happened here. Another thing to note, when the base is higher, your exponential is steeper. All right? When base is 1, you get a horizontal line. Why? Because 1 power any exponent is 1. So that's a constant function. All right? So when base is bigger than 1, you are increasing. You are increasing. When base is less than 1, you are decreasing. All right? And notice, either case, you have a horizontal asymptote with the x-axis. So let's, by the way, they all go through the point 0, 1. That's your y-intercept. Okay? So let's go through these remarks. Y-intercept for any exponential function is 0, 1. The function is positive valued with horizontal asymptote y equals 0. So look, all the graphs are above. Well, exponential, no matter what exponential, you are never going to be negative valued. Yeah, 2 power anything is going to be positive. 1 power anything is 1. 3 power anything is going to be positive, likewise 1/3 or 1/2 power. So, first of all, it's positive valued. And other than this constant function, all these other functions have horizontal asymptote x-axis. X-axis is nothing but the line y equals 0. Now, this seems to be an incomplete sentence. Let's continue here. When b is greater than 1, the function is an increasing function. When b is less than 1, the function is a decreasing function. So, increasing, increasing, decreasing, decreasing. So, when the base is less than 1, but still positive, you are decreasing. When base is greater than 1, positive, you are increasing. Okay?